On any given training flight in the early 1960s, a Lockheed F-104 starfighter performed exactly as its engineers intended. Control surfaces responded with precision. Engine parameters remained within specifications. Flight characteristics matched wind tunnel predictions. The aircraft represented the pinnacle of supersonic design philosophy, maximum performance extracted from minimum airframe through uncompromising aerodynamic efficiency. Yet pilots consistently reported an absence of trust in the machine beneath them. This was not mechanical unreliability in the conventional sense. Systems functioned. Instruments provided accurate readings. The aircraft delivered its promised performance envelope. The problem lay deeper, embedded within design assumptions that prioritized theoretical optimization over human operational reality. The F-104's flight characteristics demanded techniques that contradicted every intuitive response pilots had developed through thousands of hours on conventional aircraft. Its razor-thin wing generated lift through principles that became counterproductive at the precise moments when pilot instinct demanded familiar solutions. Recovery procedures that worked reliably on other aircraft became sources of additional hazard when applied to the starfighter's unforgiving aerodynamic personality. The engineering was sophisticated. The performance was exceptional. The aircraft operated within its design parameters consistently. But the human-machine interface created systematic conditions where correct piloting technique and aircraft survival requirements existed in fundamental opposition. How can an aircraft function perfectly according to its design, while simultaneously making pilot survival dependent on abandoning proven aviation principles? The answer lies within the fundamental design premise that guided every decision in the F-104's development. In 1952, the United States Air Force issued a requirement for a daylight air superiority fighter that subordinated all other criteria to flight performance. This singular focus shaped C.L. Kelly Johnson's approach at Lockheed's Skunk Works, where design teams examined scores of configurations including delta wings, swept wings, flush cockpits, wingtip-mounted vertical fins, rocket propulsion, low-mounted horizontal stabilizers, and V windshields. The configuration that emerged represented a radical departure from conventional aerodynamic thinking. Where other designers accepted performance compromises to maintain familiar handling characteristics, Johnson's team pursued absolute optimization within the supersonic flight regime. The resulting aircraft featured wing geometry so extreme that it violated nearly every established principle of safe aircraft design. The F-104's wing extended merely 7.5 feet from each side of the fuselage, creating an aspect ratio so low that conventional aerodynamic theory suggested it should not generate sufficient lift for controlled flight. The wing's thickness ratio of 3.26% represented the absolute minimum possible while maintaining structural integrity. Maximum thickness of 4.2 inches adjacent to the fuselage slimmed to only 1.96 inches at the tips. These dimensions created a wing that functioned more as a controllable lifting blade than a conventional airfoil. The extreme geometry served specific engineering objectives. Thin sections minimized drag rise through the transonic region. Short span reduced bending moments and structural weight. Sharp leading edges eliminated buffeting and tucking effects common in swept-wing designs at high Mach numbers. Every dimensional parameter was optimized for supersonic performance, with no concessions to subsonic handling characteristics. But these optimizations created aerodynamic behavior that fundamentally differed from any aircraft pilots had previously encountered. The thin wing generated lift through mechanisms that operated most efficiently at high speeds and high angles of attack. At lower speeds, particularly during approach and landing phases, the wing's ability to maintain attached airflow became critically dependent on precise energy management techniques that contradicted standard piloting practices. The design team addressed this challenge through the implementation of a boundary layer control system that used highly compressed air from the engine, ducted into the wing, and expelled through 55 slots positioned 0.9 inches apart along the trailing edge flap hinge line. Each slot measured 0.09 inches deep and 0.55 inches wide along the 47-inch flap length. This system added energy to boundary layer air and reduced turbulence due to flow separation, effectively extending the wing's operational envelope into lower speed regimes. However, the boundary layer control system created a fundamental dependency that pilots could not directly perceive. The wing's lifting capability at approach speeds became contingent upon engine operation and precise throttle management. Unlike conventional aircraft where engine failure primarily affected forward motion, an F-104 with engine failure lost not only thrust, but also the aerodynamic foundation for controlled flight at low speeds. This dependency was not immediately apparent to pilots, who were trained to consider engine failure as a power problem rather than a fundamental flight control emergency. The wing's anhedral configuration introduced additional complexity that challenged pilot intuition. Where conventional aircraft featured dihedral angles that provided inherent stability, the F-104's wings were angled downward approximately 10 degrees below horizontal. This cathedral configuration was necessary to counteract excessive roll effects generated by the aircraft's high-mounted horizontal stabilizer during sideslip conditions. The anhedral created roll-pitch coupling effects that made the aircraft's response to control inputs fundamentally different from conventional designs. When pilots encountered unusual attitudes or approached stall conditions, their instinctive control inputs often exacerbated rather than corrected the situation. The anhedral wing configuration meant that efforts to level the aircraft through aileron inputs could induce pitch changes that drove the aircraft deeper into stall regimes. Recovery techniques that were automatic responses for experienced pilots became sources of additional hazard when applied to the F-104's unconventional flight dynamics. The horizontal stabilizer arrangement compounded these challenges. The entire horizontal surface moved as a unit rather than employing separate elevators. This all-moving stabilizer provided exceptional control authority at high speeds, but created response characteristics that felt unfamiliar to pilots accustomed to conventional elevator systems. The stabilizer's position, only 11 inches below the top of the vertical fin, created aerodynamic interactions that affected pitch response in ways that contradicted pilot expectations based on previous aircraft experience. Landing gear integration presented additional evidence of the design philosophy's prioritization of performance over conventional considerations. Both nose and main landing gear retracted into the fuselage because the wing was too thin to accommodate conventional gear stowage. This arrangement required complex retraction mechanisms that added weight and complexity while eliminating the structural advantages typically gained from wing-mounted gear. The decision reflected the absolute nature of the design team's commitment to aerodynamic optimization. Regardless of the operational complications it created, the structural design revealed similar prioritization patterns. The wings attached to the fuselage through 5 heavy forged fittings connected to wing skins and intermediate channels. Upper and lower skins were formed from single machine-tapered plates measuring 0.25 inches thick at the root and tapering to 0.125 inches thick outboard. No cordwise ribs were employed. Instead, root and tip forgings, combined with 12 spanwise intermediate channels, formed a torsion box that provided structural integrity while maintaining the wing's knife-edge profile. This structural approach created wings that were exceptionally strong within their designed load parameters, but offered no margin for operational stresses outside the calculated envelope. Conventional wing structures incorporated safety factors that allowed pilots to exceed design limitations during emergency situations. The F-104's wing structure provided no such operational flexibility. Pilots who attempted to use control authority beyond the aircraft's design parameters found themselves operating an aircraft whose structure could not accommodate the survival techniques they had learned on conventional designs. The engine integration exemplified the design team's systematic prioritization of performance metrics over operational familiarity. The General Electric J79 engine was selected for its thrust-to-weight ratio, small frontal area, and afterburning capability. The engine's variable pitch, stator blades, adjusted automatically to prevent stall problems at low speeds and maintain compressor efficiency under all flight conditions. However, these automatic adjustments created engine behavior that was invisible to pilots and fundamentally different from the direct throttle response characteristics of conventional aircraft. The engine's automatic systems created operational dependencies that pilots could not directly control or monitor. Variable stator adjustments affected not only engine performance but also the boundary layer control system's effectiveness. Changes in engine operating conditions directly influenced the wing's aerodynamic characteristics in ways that were not reflected in conventional engine instruments. Pilots found themselves flying an aircraft whose lift generation capability was continuously modified by automatic systems, operating beyond their direct perception or control. Air inlet design reflected the same optimization philosophy. The spiked cone intake system provided maximum ram recovery for the engine at high supersonic speeds through control of shockwave formation at the inlet. This system required precise airflow management and could not tolerate the kind of operational variations that conventional inlets accommodated routinely. Pilots who deviated from precise airspeed and altitude parameters found their aircraft experiencing inlet unstart conditions that affected both engine operation and the boundary layer control system simultaneously. The cockpit design reflected assumptions about pilot adaptation that proved problematic in operational practice. Instruments were arranged on 4 vertically mounted panels with individual face lighting and edge-lighted placards. While this arrangement provided excellent visibility under ideal conditions, it created information processing challenges during high workload phases of flight. The layout assumed pilots could successfully integrate multiple information sources while managing the aircraft's unique handling characteristics under time pressure. The flight control system design embodied assumptions about pilot capability that proved incompatible with the aircraft's aerodynamic characteristics. The aircraft featured fully powered controls with artificial feel systems intended to provide pilots with familiar control sensations. However, the artificial feel system could not accurately reproduce the aerodynamic feedback that pilots relied upon to assess aircraft state and predict aircraft response to control inputs. Pilots found themselves flying an aircraft that felt conventional while behaving in fundamentally unconventional ways. Emergency procedures design reflected similar assumption patterns. Standard emergency checklists and procedures were developed based on conventional aircraft behavior patterns. These procedures assumed that pilots would have sufficient time and control authority to execute methodical recovery techniques. The F-104's handling characteristics compressed decision-making timeframes and reduced control authority margins in ways that made conventional emergency procedures ineffective or counterproductive. The ejection seat system selection revealed the design team's recognition of the aircraft's fundamental limitations while simultaneously demonstrating their assumption that these limitations could be managed through technology rather than design modification. Original F-104 aircraft featured downward ejecting seats based on the assumption that ejections would occur at high altitudes where clearance below the aircraft was available. The subsequent development of upward ejecting seats acknowledged the aircraft's tendency to encounter emergency situations at low altitudes where downward ejection was not survivable. However, even the improved ejection system incorporated assumptions about pilot decision-making capability and aircraft behavior that proved problematic in operational practice. The ejection sequence required precise timing and aircraft attitude management that was difficult to achieve given the F-104's handling characteristics during emergency situations. Pilots found themselves operating an aircraft where the emergency escape system demanded performance standards that the aircraft's behavior patterns made difficult to achieve. The development testing program reflected institutional assumptions about the transferability of pilot expertise from conventional aircraft to the F-104's unique operational requirements. Test pilot feedback focused primarily on performance validation rather than operational suitability assessment. The testing regimen assumed that once basic flight characteristics were documented, operational pilots could adapt their techniques to accommodate the aircraft's unique requirements through training and experience. This assumption failed to recognize that the F-104's design created situations where adaptation was not possible through technique modification alone. The aircraft's fundamental characteristics created operational scenarios where pilot survival depended on abandoning proven techniques rather than refining them. The aircraft demanded not just different piloting techniques, but entirely different conceptual frameworks for understanding the relationship between pilot inputs and aircraft response. The design philosophy that created the F-104 represented an extreme application of engineering optimization principles that assumed human operational factors could be subordinated to technical performance without creating systematic safety problems. Every major design decision prioritized aerodynamic efficiency over operational flexibility, control authority over handling predictability, and performance capability over pilot familiarity. These design choices created an aircraft that functioned exceptionally well within its intended operational envelope while becoming systematically hazardous when operational requirements forced pilots to operate outside those parameters. The F-104's design premise assumed that operational flexibility could be maintained through pilot adaptation rather than design accommodation, creating the foundation for the systematic human-machine interface problems that would define the aircraft's operational history. The institutional response to these design characteristics reflected a fundamental misunderstanding of the relationship between pilot expertise and aircraft systems. Rather than recognizing that the F-104's unique characteristics required fundamentally different operational approaches, training organizations assumed that conventional pilot development programs could be modified to accommodate the aircraft's unusual requirements. This assumption created systematic conditions where highly qualified pilots were prepared for an aircraft that did not exist, while remaining unprepared for the aircraft they would actually fly. Beginning in 1956, Lockheed and the United States Air Force conducted an extensive flight test program involving 52 test aircraft and approximately 6,500 missions at a cost exceeding $30 million. The program's scope reflected the institutional recognition that the F-104 represented a significant departure from conventional aircraft design. However, the testing focus remained primarily on performance validation rather than operational suitability assessment. Test pilots concentrated on documenting the aircraft's capabilities within its design envelope rather than identifying the systematic challenges that operational pilots would encounter when required to operate outside those parameters. The test program's findings were interpreted through institutional frameworks that assumed pilot adaptation could bridge any gaps between aircraft characteristics and operational requirements. When test pilots reported unusual handling characteristics, these reports were processed as training requirements rather than fundamental design limitations. The institutional response focused on developing specialized techniques to manage the aircraft's behavior rather than questioning whether the aircraft's behavior was compatible with operational safety requirements. This interpretation framework reflected deeper institutional assumptions about the relationship between technology and human performance. Military aviation culture emphasized pilot adaptation as the primary mechanism for integrating new aircraft capabilities into operational service. The underlying assumption was that pilot skill and training could overcome any aircraft limitations, provided the training was sufficiently comprehensive and rigorous. This assumption had proven valid for previous aircraft developments where new technologies enhanced rather than replaced fundamental piloting principles. The F-104 represented a qualitative departure from this assumption framework. The aircraft's characteristics did not simply require enhanced versions of conventional techniques. They demanded abandonment of techniques that had proven reliable across multiple aircraft types and operational scenarios. Pilots were required to develop entirely new conceptual frameworks for understanding the relationship between aircraft energy state, control inputs, and aircraft response. The training challenge was not skill enhancement, but cognitive restructuring. Training programs failed to recognize this fundamental difference. Transition courses focused on familiarizing pilots with the F-104's performance characteristics and operational procedures, while assuming that underlying piloting principles remained applicable. Pilots learned to manage the aircraft's systems and operate within its performance envelope, but they did not learn to abandon the decision-making frameworks that had proven successful on conventional aircraft. The training methodology reflected institutional assumptions about pilot learning that proved incompatible with the F-104's operational requirements. Training sequences assumed that pilots could successfully integrate new aircraft characteristics into existing knowledge frameworks through progressive exposure and practice. This approach worked effectively for aircraft that represented evolutionary developments of established design principles. However, the F-104's characteristics were not evolutionary, they were revolutionary in ways that made previous experience a liability rather than an asset. Simulator training programs exemplified these flawed assumptions. Early F-104 simulators focused on replicating the aircraft's performance characteristics and system behaviors while inadequately addressing the decision-making challenges that pilots would encounter during emergency situations. Simulator scenarios emphasized procedural execution, rather than the fundamental cognitive adjustments required to operate an aircraft whose behavior contradicted established piloting principles. The simulator training approach assumed that muscle memory and procedural familiarity would provide adequate preparation for managing emergency situations. This assumption failed to account for the psychological stress effects that occur when familiar control inputs produce unfamiliar aircraft responses. During actual emergency situations, pilots found themselves operating an aircraft that felt conventional while behaving unconventionally, creating cognitive conflicts that interfered with effective decision-making. Cockpit resource management training reflected similar assumption patterns. Training programs assumed that conventional crew coordination principles would remain applicable to F-104 operations despite the aircraft's single-pilot configuration and unique handling characteristics. When two-seat trainer versions were developed, training programs focused on conventional instructor-student relationships rather than addressing the specialized knowledge requirements for managing the F-104's unusual characteristics during instructional flights. The instructor training program revealed institutional assumptions about expertise transferability that proved problematic in operational practice. Experienced pilots who had demonstrated exceptional competence on conventional aircraft were assumed to possess the foundation necessary for effective F-104 instruction. However, instructor effectiveness required not only personal mastery of the F-104's unique characteristics but also the ability to help other pilots abandon successful techniques that had proven reliable on conventional aircraft. Many instructors found themselves in the position of teaching techniques that contradicted their own experiential knowledge base. They were required to demonstrate confidence in procedures that felt fundamentally wrong based on their accumulated flying experience. This created instructional environments where both instructors and students were operating outside their comfort zones without adequate institutional support for managing the psychological challenges involved. The check flight and proficiency evaluation system reflected assumptions about pilot competence that failed to address the F-104's unique requirements. Standard evaluation criteria focused on procedural compliance and performance parameter achievement, rather than assessing pilots' ability to manage the cognitive conflicts created by the aircraft's unusual handling characteristics. Pilots could demonstrate technical proficiency while remaining unprepared for the decision-making challenges they would encounter during emergency situations. Emergency procedure training exemplified the systematic nature of these institutional failures. Standard emergency procedures were developed based on conventional aircraft behavior patterns and assumed that pilots would have sufficient time and control authority to execute methodical recovery techniques. The F-104's handling characteristics compressed decision-making timeframes and reduced control authority margins in ways that made conventional emergency procedures ineffective or counterproductive. Training programs taught emergency procedures as discrete skill sets rather than integrated decision-making frameworks. Pilots learned to execute specific responses to specific emergencies without developing the conceptual understanding necessary to adapt these procedures when actual emergency conditions differed from training scenarios. This approach created systematic preparation for emergency situations that did not accurately reflect the emergency conditions that the F-104's characteristics were likely to create. The maintenance training program revealed additional institutional assumptions that created operational vulnerabilities. Maintenance personnel were trained to service aircraft systems based on conventional reliability expectations and failure mode patterns. The F-104's unique characteristics created maintenance requirements and failure patterns that differed systematically from conventional aircraft. However, maintenance training programs focused on procedural compliance rather than developing the understanding necessary to recognize when conventional maintenance approaches were inadequate for the F-104's specialized requirements. Ground crew training reflected similar assumption patterns. Personnel responsible for aircraft servicing and ground operations were trained according to conventional protocols that assumed standardized aircraft behavior and response characteristics. The F-104's unique ground handling characteristics and operational limitations required specialized knowledge and procedures that were inadequately addressed in standard training programs. The institutional approach to pilot selection revealed assumptions about the relationship between pilot experience and F-104 compatibility that proved systematically flawed. Selection criteria emphasized conventional piloting excellence rather than assessing pilot psychological flexibility and adaptability to unconventional aircraft behavior. Pilots who had achieved the highest levels of success on conventional aircraft often experienced the greatest difficulty adapting to the F-104's requirements because their expertise was based on principles that became liabilities in the F-104 operational environment. The training schedule and progression assumptions reflected institutional beliefs about learning timelines that proved incompatible with the cognitive restructuring required for safe F-104 operations. Training programs assumed that pilots could achieve operational competence within timeframes that had proven adequate for conventional aircraft transitions. However, the F-104 required not just skill development but fundamental conceptual reorientation that demanded significantly longer development periods than institutional schedules accommodated. Performance evaluation metrics reflected institutional assumptions about competence demonstration that failed to address the F-104's unique operational challenges. Evaluation criteria focused on technical skill demonstration, rather than assessing pilot psychological preparation for managing the stress and decision-making challenges created by the aircraft's unusual characteristics. Pilots could demonstrate technical proficiency while remaining psychologically unprepared for the operational realities of F-104 flight. The training program's approach to risk management reflected institutional assumptions about accident prevention that proved inadequate for the F-104's operational environment. Training focused on procedural compliance and skill development while inadequately addressing the fundamental risk factors created by the aircraft's design characteristics. The institutional assumption was that accidents could be prevented through enhanced training and improved procedures, rather than recognizing that the aircraft's characteristics created risk levels that could not be eliminated through human performance improvements alone. Documentation and knowledge transfer systems reflected assumptions about institutional learning that failed to capture the specialized knowledge required for safe F-104 operations. Standard documentation focused on procedural information rather than the experiential knowledge necessary for managing the aircraft's unique characteristics. Informal knowledge transfer between experienced and inexperienced pilots was inadequate to bridge the gap between documented procedures and the practical understanding required for operational success. The institutional culture surrounding F-104 operations reflected assumptions about pilot resilience and adaptability that created additional stress factors for operational personnel. The aircraft's reputation created psychological pressures that interfered with effective learning and performance. Pilots were expected to demonstrate confidence and competence while operating an aircraft that was widely acknowledged to be exceptionally challenging and unforgiving. These cultural factors interacted with the aircraft's technical characteristics to create operational environments where pilots faced simultaneous technical and psychological challenges that exceeded the preparation provided by conventional training programs. The institutional response focused on technical training enhancements rather than addressing the psychological support requirements created by the aircraft's unique characteristics and operational reputation. The systematic failures embedded within training doctrine and institutional assumptions manifested most clearly during routine flight operations, where the gap between pilot preparation and aircraft behavior became operationally significant. The transition from training environments to operational flight revealed the extent to which institutional assumptions about pilot adaptation had failed to address the fundamental incompatibilities between conventional piloting expertise and F-104 operational requirements. Routine training flights at facilities like Myrtle Beach Army Air Base demonstrated how the convergence of design limitations and institutional preparation failures created predictable operational hazards. These flights occurred under controlled conditions with experienced pilots operating familiar aircraft, yet they consistently produced situations where pilot expertise became a liability rather than an asset. The pattern of incidents during training operations revealed systematic problems that extended beyond individual pilot error or mechanical failure. The approach and landing phase emerged as the critical operational regime where the F-104's design characteristics and pilot preparation failures converged most dramatically. The aircraft's approach speed requirement of 150 miles per hour created operational conditions that fundamentally challenged conventional piloting principles. This speed represented nearly double the approach speeds that pilots had learned to associate with safe landing operations, creating psychological and physiological stress factors that interfered with effective decision-making. The high approach speed requirement was not arbitrary. It reflected the aerodynamic necessities created by the aircraft's wing design. The thin wing's lift characteristics required high-energy flight conditions to maintain adequate control authority and stall margins. Below 150 miles per hour, the wing's ability to generate sufficient lift became critically dependent on the boundary layer control system and precise angle of attack management. However, these dependencies were not immediately apparent to pilots, who perceived the high approach speed as an operational limitation rather than a fundamental flight safety requirement. Pilot workload during approach phases exceeded the cognitive processing capabilities that conventional training had developed. The combination of high approach speeds, compressed decision-making timeframes, and unfamiliar control response characteristics created information processing demands that overwhelmed standard pilot decision-making frameworks. Pilots found themselves required to process multiple information streams simultaneously while managing an aircraft that responded to control inputs in ways that contradicted their experiential expectations. The sensory feedback mechanisms that pilots relied upon for aircraft state assessment became systematically misleading during F-104 approach operations. Conventional aircraft provided pilots with tactile, visual, and auditory cues that enabled accurate assessment of aircraft energy state, control authority margins, and developing emergency conditions. The F-104's artificial control feel systems and unique aerodynamic characteristics created sensory environments where these familiar cues provided inaccurate or contradictory information. Pilots experienced control forces and aircraft responses that felt conventional, while reflecting aerodynamic conditions that were fundamentally different from conventional aircraft behavior. The artificial feel system created the sensation of normal control authority, while the aircraft was operating near the margins of controllable flight. This sensory disconnection created decision-making environments where pilots' situational awareness was systematically compromised without their recognition. The energy management requirements for safe F-104 approaches demanded techniques that contradicted fundamental piloting principles that had proven reliable across multiple aircraft types. Conventional energy management emphasized maintaining adequate airspeed margins above stall speeds and reducing power during approach phases to control descent rates and approach profiles. The F-104's characteristics required pilots to maintain continuous high power settings and precise airspeed control throughout approach phases, eliminating the energy management flexibility that pilots relied upon for safety margins. When pilots encountered approach situations that deviated from ideal conditions, their instinctive responses often created additional hazards rather than improving safety margins. The tendency to reduce power in response to excessive approach speeds or unstable approach conditions became dangerous when applied to F-104 operations. Power reductions below critical thresholds compromised both engine thrust and boundary layer control system effectiveness, creating simultaneous losses of forward motion capability and lift generation capacity. Control input timing became critical in ways that exceeded conventional pilot response capabilities. The F-104's control system response characteristics created situations where the timing of pilot inputs was as important as their magnitude and direction. Control inputs that would be appropriate at one phase of an approach sequence became inappropriate or dangerous if applied at slightly different phases of the same sequence. This timing sensitivity exceeded the precision that pilots could reliably maintain under operational stress conditions. The aircraft's stall characteristics created operational scenarios where conventional recovery techniques became systematically counterproductive. When pilots encountered approaching stall conditions, their trained responses emphasized immediate angle of attack reduction and power application. However, the F-104's thin wing and high loading characteristics meant that angle of attack reduction during certain flight phases resulted in immediate loss of lift, without providing adequate time for power application to become effective. The stall progression patterns of the F-104 differed fundamentally from conventional aircraft behavior. Conventional aircraft typically provided pilots with predictable stall warning indications and recovery characteristics that allowed methodical application of standard recovery techniques. The F-104's stall progression was rapid and often asymmetric, creating departure conditions that developed faster than pilot recognition and response capabilities could address. Recovery from unusual attitudes required techniques that contradicted the fundamental principles that pilots had learned for managing similar situations on conventional aircraft. The aircraft's anhedral wing configuration and high-loading characteristics created roll-pitch coupling effects that made conventional recovery techniques ineffective or dangerous. Pilots who attempted to apply standard unusual attitude recovery procedures often found these techniques driving the aircraft deeper into uncontrollable flight regimes. The time compression effects during emergency situations exceeded the decision-making capabilities that training programs had developed. Emergency conditions in conventional aircraft typically provided pilots with sufficient time to recognize problems, assess options, and execute appropriate responses. The F-104's characteristics compressed these time frames to intervals that were inadequate for methodical decision-making processes. Pilots were required to make critical decisions based on incomplete information within time frames that exceeded their trained response capabilities. Engine failure scenarios exemplified the systematic nature of these operational challenges. Conventional aircraft training emphasized engine failure as primarily a power loss emergency that could be managed through established procedures focused on airspeed control, landing site selection, and methodical approach execution. F-104 engine failures created simultaneous thrust loss and boundary layer control system failure, effectively converting engine emergencies into fundamental flight control emergencies that required immediate and precise pilot responses. The psychological factors associated with engine failure management became systematically problematic during F-104 operations. Pilots were trained to respond to engine failures with deliberate, methodical procedures that emphasized maintaining aircraft control while executing appropriate emergency responses. The F-104's characteristics required immediate and precise pilot responses that left no time for deliberate analysis or methodical procedure execution. This created decision-making environments where pilot psychology worked against operational safety rather than supporting it. Spatial disorientation incidents revealed the extent to which the F-104's characteristics created perceptual challenges that exceeded conventional pilot preparation. The aircraft's high-performance envelope and unusual handling characteristics created flight environments where pilots lost situational awareness more readily than conventional aircraft operations would predict. The combination of high speeds, unusual attitudes, and unfamiliar control responses created conditions where pilots became confused about aircraft state and control requirements. Weather-related operational challenges demonstrated how the F-104's design characteristics interacted with environmental factors to create operational hazards that conventional training had not addressed. The aircraft's high approach speeds and precise control requirements made it exceptionally sensitive to wind conditions and atmospheric disturbances that conventional aircraft could accommodate routinely. Pilots found themselves operating an aircraft that required environmental conditions more precise than operational environments could reliably provide. Formation flying operations revealed additional operational challenges that reflected the systematic nature of the F-104's human factors problems. The aircraft's unique handling characteristics and high-performance envelope created formation flying requirements that exceeded conventional pilot capabilities. Formation operations required pilots to maintain precise aircraft control while simultaneously managing the additional workload associated with formation maintenance. The F-104's characteristics made this combination of tasks exceptionally demanding and created systematic risks during routine formation operations. Night operations exemplified how the F-104's operational challenges were magnified by reduced pilot sensory capabilities. The aircraft's high approach speeds and precise control requirements became even more demanding when pilots were operating with reduced visual references and increased psychological stress associated with night flying. The combination of challenging aircraft characteristics and reduced environmental support created operational conditions that exceeded pilot capabilities more readily than daylight operations. The incident patterns that emerged from operational experience revealed the systematic nature of the problems created by the convergence of design limitations and institutional preparation failures. Rather than random mechanical failures or isolated pilot errors, incident reports documented consistent patterns of pilot-aircraft interaction problems that occurred across multiple aircraft pilots and operational scenarios. These patterns indicated fundamental compatibility problems between aircraft characteristics and pilot capabilities that could not be resolved through individual training or procedural improvements. Pilot reports from operational units documented systematic difficulties with aircraft state awareness during critical phases of flight. Pilots consistently reported that the aircraft's behavior did not match their expectations based on control inputs and instrument indications. These reports indicated that the aircraft's artificial control field systems and unusual aerodynamic characteristics created systematic mismatches between pilot perception and actual aircraft state that interfered with effective flight management. The geographic distribution of incidents reflected operational factors rather than random patterns, indicating that specific operational environments created systematic challenges for F-104 operations. Bases with challenging approach conditions, adverse weather patterns, or operational tempo demands experienced incident rates that exceeded statistical expectations for random failures. This geographic clustering indicated that the aircraft's operational limitations interacted with environmental and operational factors to create systematic safety challenges. Seasonal patterns and incident reports revealed how environmental conditions affected the aircraft's operational safety margins. The F-104's sensitive handling characteristics and precise control requirements made it more susceptible to seasonal weather variations than conventional aircraft. Changes in atmospheric density, wind patterns, and visibility conditions created operational challenges that exceeded pilot adaptation capabilities and aircraft design margins. The evolution of pilot techniques and unofficial procedures documented how operational personnel attempted to develop solutions for the systematic problems they encountered. These informal adaptations represented pilot recognition that conventional techniques were inadequate for safe F-104 operations. However, the informal nature of these adaptations meant that solutions developed by experienced pilots were not systematically transferred to other pilots, creating inconsistent preparation levels across the pilot community. The physical mechanisms underlying these operational challenges revealed themselves most clearly through analysis of the aircraft's fundamental aerodynamic behavior during departure from controlled flight. The F-104's unique configuration created stall progression patterns that differed so dramatically from conventional aircraft that pilots trained on standard stall recognition and recovery techniques found themselves systematically unprepared for the aircraft's actual behavior during loss of control situations. The thin wing's stall characteristics represented a fundamental departure from the gradual, predictable stall progression that formed the foundation of conventional pilot training. Where conventional wings provided pilots with progressive warning signs including buffeting, reduced control effectiveness, and predictable brake characteristics, the F-104's wing exhibited what aerodynamic analysis revealed to be an essentially binary transition between attached and separated airflow. This transition occurred with minimal warning and progressed too rapidly for conventional pilot recognition and response capabilities. The physics underlying this behavior stemmed directly from the wing's extreme geometric parameters. The 3.26% thickness ratio created airfoil sections that maintained attached flow through very limited angle of attack ranges. Unlike conventional wings that experienced gradual flow separation beginning at the trailing edge and progressing forward, the F-104's thin sections experienced nearly simultaneous flow separation across large portions of the wing surface when critical angle of attack values were exceeded. This aerodynamic behavior created stall progression patterns that violated fundamental assumptions embedded in pilot training doctrine. Conventional stall training emphasized recognition of approaching stall conditions through tactile, visual, and auditory cues that provided pilots with adequate warning time to execute recovery procedures. The F-104's stall progression compressed these warning periods to intervals that were inadequate for pilot recognition, much less methodical recovery execution. The boundary layer control system's integration into the wing's lift generation mechanism created additional complexity that pilots could not directly assess or control. The system's 55 slots along the trailing edge flap hinge line provided artificial energy to maintain attached flow under conditions where the natural airflow would separate. However, the system's effectiveness depended on precise engine operation and throttle management in ways that were not immediately apparent to pilots operating under high workload conditions. When boundary layer control system effectiveness decreased due to engine power reductions or system malfunctions, the wing stall characteristics changed dramatically, without providing pilots with clear indication of the system degradation. Pilots found themselves operating an aircraft whose fundamental flight characteristics could change suddenly and without warning based on system conditions that were not directly monitored or controlled through primary flight instruments. The anhedral wing configuration created roll-pitch coupling effects that made stall recovery systematically more complex than conventional aircraft training had prepared pilots to manage. When one wing section stalled before the other, which was common given the aircraft's operational loading patterns, the resulting roll motion was coupled with pitch changes that drove the aircraft deeper into stalled conditions, rather than providing the pilot with clear directional information about recovery requirements. Conventional stall recovery training emphasized opposite aileron and forward elevator inputs as primary recovery techniques. However, the F-104's roll-pitch coupling meant that aileron inputs during stalled conditions often exacerbated the stall rather than assisting recovery. Pilots who applied conventional recovery techniques found their control inputs driving the aircraft into more severe departure conditions, rather than toward controlled flight recovery. The aircraft's high wing loading created stall characteristics that violated fundamental assumptions about energy management and recovery techniques. Conventional aircraft training emphasized that adequate airspeed provided pilots with sufficient control authority and recovery margins for managing stall situations. The F-104's high wing loading meant that conventional recovery airspeeds were inadequate for maintaining control authority during stall conditions. The relationship between airspeed and control authority in the F-104 was fundamentally different from conventional aircraft, where increased airspeed typically provided enhanced control effectiveness on conventional aircraft. The F-104's control authority remained critically dependent on angle of attack management, even at high airspeeds. This created operational scenarios where pilots who maintained adequate airspeed according to conventional training standards found themselves with inadequate control authority for managing developing stall conditions. The all-moving horizontal stabilizer configuration created pitch control characteristics that differed significantly from conventional elevator systems in ways that became critical during stall recovery attempts. The stabilizer's high position and interaction with the aircraft's wake patterns meant that pitch control authority degraded rapidly during stall conditions. Pilots found themselves with inadequate pitch control for executing conventional recovery techniques even when they recognized developing stall conditions in time to attempt recovery. The aircraft's center of gravity position and mass distribution created stability characteristics that worked against pilot recovery efforts during stall conditions. Unlike conventional aircraft that exhibited natural pitch-down tendencies during stalls that assisted pilot recovery efforts. The F-104's configuration created pitch-up tendencies that required active pilot inputs to prevent deepening stall conditions. This behavior pattern contradicted pilot expectations based on conventional aircraft experience and created additional workload during emergency situations when pilot capabilities were already at maximum levels. Engine response characteristics during stall situations created additional complications that exceeded pilot management capabilities. The J-79 engine's variable stator vane system and complex control logic meant that power application during stall recovery attempts did not produce the immediate thrust response that pilots expected based on conventional aircraft experience. The engine's response lag created situations where pilots who applied appropriate power inputs found these inputs ineffective due to timing factors that were beyond their control or prediction capability. The interaction between engine power settings and boundary layer control system effectiveness created feedback loops that pilots could not directly assess or manage. Power reductions that pilots might apply to manage approach profiles or respond to perceived overspeed conditions could simultaneously reduce boundary layer control effectiveness and degrade the wing's stall characteristics. These interactions were not immediately apparent to pilots and created situations where appropriate responses to one aspect of aircraft control became inappropriate for overall flight safety. Recovery from fully developed stalls required techniques that were not only different from conventional procedures, but were essentially opposite to conventional pilot training. Where conventional recovery emphasized immediate angle of attack reduction followed by power application, F-104 stall recovery often required precise power management before angle of attack changes could be effective. This sequencing requirement exceeded the precision that pilots could maintain during high-stress emergency situations. The aircraft's departure characteristics during asymmetric stalls created unrecoverable flight conditions that developed too rapidly for pilot intervention. When stall progression was not symmetric across both wings, the resulting roll and yaw motions coupled with the aircraft's unusual stability characteristics to create departure modes that exceeded both pilot recognition capabilities and aircraft control authority margins. These departures progressed through phase transitions that made recovery impossible once initial departure conditions were established. Spin characteristics represented perhaps the most dramatic example of the aircraft's fundamental incompatibility with conventional pilot training and response capabilities. The F-104's configuration created spin modes that were fundamentally unrecoverable using conventional techniques. The aircraft's high wing loading, unusual stability characteristics, and control authority limitations meant that once spin conditions were established, pilot inputs were insufficient to restore controlled flight regardless of technique or timing. The spin progression patterns violated fundamental assumptions about aircraft behavior that formed the foundation of military pilot training. Conventional spin training emphasized that spins were recoverable flight conditions that could be managed through methodical application of appropriate control inputs. The F-104's spin characteristics created flight conditions where pilot survival depended on ejection rather than flight recovery, fundamentally challenging the basic assumption that pilots could recover their aircraft from any flight condition through appropriate technique and control inputs. Ground effect phenomena during landing approaches created additional aerodynamic complications that pilots could not anticipate or manage effectively. The aircraft's unusual wing characteristics and boundary layer control system created ground effect patterns that differed significantly from conventional aircraft behavior. These differences could cause sudden changes in aircraft sink rate, control authority, and stall characteristics during critical phases of landing approaches, when pilots had minimal altitude margins for managing unexpected aircraft behavior. The interaction between ground effect and boundary layer control system effectiveness created particularly hazardous conditions during go-around attempts. When pilots attempted to execute go-around procedures from low-altitude approaches, the transition out of ground effect often coincided with increased power demands on the boundary layer control system at precisely the moment when engine acceleration lag created temporary reductions in system effectiveness. This timing created critical phases where aircraft control margins were reduced at the worst possible moment from an operational standpoint. High-speed stall characteristics created operational scenarios that exceeded both pilot recognition capabilities and available recovery techniques. At high speeds, the aircraft could encounter stall conditions that were not accompanied by the traditional reduction in forward speed that pilots associated with stall situations. These high-speed stalls developed when angle of attack increased beyond critical values while airspeed remained high, creating aerodynamic conditions where conventional stall recognition techniques provided no warning of developing loss of control. The compressibility effects associated with high-speed flight created additional complications that interacted with the aircraft's fundamental stall characteristics in ways that pilots could not predict or manage. As the aircraft approached transonic speeds, shock wave formation on the wing surfaces could trigger premature flow separation that created stall conditions even when angle of attack remained within normal ranges. These compressibility-induced stalls occurred without the warning signs that pilots relied upon for stall recognition and created departure conditions that developed too rapidly for effective pilot response. Control surface effectiveness limitations during high angle of attack flight created situations where pilots retained the sensation of control authority while actually operating beyond the margins of effective aircraft control. The artificial feel systems continued to provide normal control force gradients even when actual control surface effectiveness had degraded to levels that were inadequate for maintaining controlled flight. This sensory disconnection between pilot perception and aircraft capability created decision-making environments where pilots continued attempts at aircraft control long after such attempts had become futile. The recognition of these fundamental aerodynamic limitations led to the development of emergency procedures and escape systems designed to provide pilot survival alternatives when aircraft recovery became impossible. However, the design and implementation of these secondary safety systems reflected many of the same flawed assumptions about pilot capability and aircraft behavior that had created the primary safety problems. Rather than resolving the fundamental incompatibility between pilot capabilities and aircraft characteristics, these systems created additional layers of complexity that often compounded rather than mitigated the operational hazards. The evolution of ejection seat systems for the F-104 revealed institutional recognition of the aircraft's fundamental limitations while simultaneously demonstrating continued reliance on technological solutions rather than design modifications to address safety problems. Original F-104 aircraft featured downward ejecting seats based on the assumption that emergency situations would occur at altitudes where clearance below the aircraft was available and sufficient for safe parachute deployment. This assumption reflected fundamental misunderstanding of the operational scenarios that the aircraft's characteristics were most likely to create. The F-104's handling difficulties occurred primarily during low-altitude phases of flight, including approach, landing, and low-altitude training operations. These operational scenarios provided precisely the conditions where downward ejection was least survivable, yet they represented the most common emergency situations that pilots actually encountered. The institutional response to this problem involved development of upward ejecting seat systems rather than recognition that the aircraft's operational characteristics created systematic emergency situations that exceeded the capabilities of any ejection system to resolve safely. The C-2 ejection seat represented advanced pyrotechnic technology designed to provide reliable pilot extraction from the aircraft under a wide range of flight conditions. However, the seat's operational requirements assumed pilot decision-making capabilities and aircraft attitude control that were often unavailable during actual F-104 emergency situations. The ejection sequence timing requirements created systematic problems that reflected fundamental mismatches between the technology's assumptions and the aircraft's actual emergency characteristics. The seat required approximately 0.3 of a second for pre-ejection functions, including foot restraint activation, knee guard positioning, and arm restraint deployment. During this period, the aircraft continued its departure progression, often transitioning through attitude and altitude conditions that degraded ejection safety margins. The rocket catapult propulsion system provided sufficient thrust to clear the aircraft structure under ideal conditions. But the definition of ideal conditions assumed aircraft attitudes and flight paths that were seldom available during actual F-104 emergencies. The aircraft's rapid departure characteristics meant that pilots often found themselves in attitudes and flight conditions where ejection trajectories would intersect with aircraft structure or result in insufficient altitude for parachute deployment. Pilot decision-making requirements during emergency situations exceeded human cognitive capabilities when operating under the stress and time compression that F-104 emergencies typically involved. The decision to eject required pilots to assess aircraft controllability, altitude margins, ejection envelope parameters, and survival prospects within timeframes that were inadequate for methodical analysis. This decision-making challenge was compounded by the psychological difficulties associated with abandoning aircraft that pilots had been trained to recover through personal skill and technique. The timing of ejection decisions created systematic problems that reflected the fundamental incompatibility between human decision-making capabilities and the aircraft's emergency characteristics. Early ejection decisions during recoverable situations resulted in unnecessary aircraft loss and pilot exposure to ejection risks. Late ejection decisions during unrecoverable situations resulted in ejection attempts outside safe envelope parameters with reduced survival prospects. Pilots faced systematic double-bind situations where continued attempts at aircraft recovery reduced ejection safety margins while premature ejection decisions contradicted their training and professional responsibilities. This psychological framework created decision-making environments where pilots often delayed ejection decisions until aircraft conditions had progressed beyond safe ejection envelope parameters. The survival kit integration with the ejection seat reflected assumptions about post-ejection survival scenarios that failed to account for the operational environments where F-104 ejections were most likely to occur. The automatic survival kit included emergency oxygen, life raft inflation systems, and survival equipment designed for conventional military operational scenarios. However, F-104 ejections typically occurred during training operations over domestic territory where survival kit effectiveness was less important than medical evacuation and rescue coordination. Emergency procedure training for ejection situations revealed systematic institutional failures to address the psychological preparation required for successful ejection decision-making. Training programs focused on mechanical ejection procedures and seat operation rather than developing the decision-making frameworks necessary for effective emergency assessment under stress conditions. Pilots learned to operate ejection systems without developing the psychological preparation necessary for making appropriate ejection timing decisions during actual emergencies. The canopy jettison system created additional complexity that increased pilot workload during emergency situations, when cognitive resources were already at maximum levels. The system provided 3 activation methods including manual handle operation, automatic activation through ejection sequence initiation, and external rescue crew operation. However, the multiple activation options created additional decision-making requirements during situations where pilot cognitive capabilities were already overwhelmed. Canopy jettison timing became critical in ways that exceeded pilot precision capabilities under emergency conditions. Premature canopy jettison created additional aerodynamic disruption that could worsen aircraft departure characteristics. Delayed canopy jettison reduced available time for ejection sequence completion and created risks of canopy interference with ejection trajectories. The timing precision required for optimal canopy jettison exceeded the capabilities that pilots could maintain under emergency stress conditions. Hydraulic system design for emergency operations reflected assumptions about system reliability and pilot management capabilities that proved inadequate during actual emergency situations. The dual hydraulic system configuration provided redundancy for normal operations, but emergency conditions often involved multiple system failures or operational scenarios where redundant systems were compromised simultaneously. The RAM air turbine emergency system provided backup hydraulic power during engine failure situations, but its deployment and operation created additional aircraft handling complications during emergency situations when pilots were already struggling to maintain control. The turbine deployment changed aircraft drag and stability characteristics in ways that affected control requirements and pilot workload during critical phases of emergency management. Emergency electrical power systems reflected similar design assumptions about pilot management capabilities during crisis situations. The emergency generator and battery systems provided power for essential systems including flight instruments, radio communications, and ejection seat operation. However, the power management requirements during emergency situations created additional pilot workload when cognitive resources were already at maximum levels. The interaction between emergency power systems and normal aircraft systems created complexity that exceeded pilot management capabilities during actual emergency situations. Emergency power activation often required pilots to reconfigure electrical systems while simultaneously managing aircraft control and emergency procedures. This multitasking requirement exceeded the cognitive capabilities that pilots could maintain under emergency stress conditions. Communication system design for emergency operations assumed that pilots would have adequate time and mental resources for radio communications during emergency situations. However, the rapid progression of F-104 emergencies often left pilots with inadequate time for standard emergency communication procedures. The compressed timeframes associated with F-104 emergencies made standard emergency communication protocols ineffective for alerting rescue services or providing situational information to ground personnel. Emergency navigation systems reflected assumptions about pilot navigation capabilities during crisis situations that proved unrealistic for actual F-104 emergency conditions. The aircraft's high-performance envelope and rapid emergency progression often left pilots with minimal time for navigation planning or position reporting during emergency situations. Emergency navigation requirements exceeded the attention resources that pilots could allocate to navigation tasks while simultaneously managing aircraft control and emergency procedures. Ground crew emergency response procedures reflected institutional assumptions about emergency situation progression that failed to account for the rapid development and compressed timeframes typical of F-104 emergencies. Standard emergency response protocols assumed that emergency situations would provide adequate time for methodical emergency service deployment and coordination. The F-104's emergency characteristics often progressed too rapidly for effective ground-based emergency response, regardless of procedure quality or personnel training. Fire suppression systems for ground emergencies reflected similar assumption problems about emergency situation management and response coordination. The aircraft's fuel system design and engine characteristics created fire hazard patterns that differed from conventional aircraft emergency characteristics. Emergency response procedures developed for conventional aircraft were often inadequate for F-104 emergency situations, due to the unique hazard patterns created by the aircraft's design and systems. Medical emergency response coordination reflected institutional assumptions about ejection survival rates and injury patterns that proved inadequate for actual F-104 emergency outcomes. Medical personnel were trained to respond to conventional aircraft emergency scenarios and ejection injuries based on previous aircraft experience. The F-104's ejection systems and emergency characteristics created injury patterns and survival scenarios that exceeded the preparation provided by conventional emergency medical training. Search and rescue coordination procedures reflected assumptions about emergency location and survival timeframes that often proved inadequate for F-104 emergency situations. The aircraft's high-performance envelope meant that emergency situations could occur at locations and under conditions that created systematic search and rescue challenges. The rapid progression of F-104 emergencies often left rescue personnel with inadequate information about emergency location and pilot status for effective rescue coordination. Weather-related emergency complications revealed how environmental factors interacted with the aircraft's emergency characteristics. to create operational hazards that exceeded emergency procedure effectiveness. The F-104's sensitive handling characteristics and precise control requirements made it particularly vulnerable to weather-related emergency situations during critical phases of flight. Emergency procedures developed for ideal weather conditions proved inadequate for weather-related emergency scenarios. Night emergency operations created additional complications that reflected the systematic nature of the problems created by the aircraft's emergency characteristics. The aircraft's emergency progression patterns were difficult enough to manage during daylight operations when pilots had maximum sensory input and situational awareness. Night operations reduced pilot sensory capabilities while maintaining the same rapid emergency progression timeframes that challenged pilot response capabilities during daylight operations. Formation flying emergency procedures revealed additional systematic problems that reflected the aircraft's fundamental incompatibility with conventional military operational requirements. Formation operations created scenarios where emergency situations in one aircraft created hazards for other formation members. The F-104's rapid emergency progression patterns often left formation pilots with inadequate time to recognize and respond to emergencies involving other formation aircraft. The institutional approach to emergency procedure development reflected continued reliance on procedural solutions, rather than recognition that the aircraft's fundamental characteristics created emergency scenarios that exceeded human management capabilities, regardless of procedure quality or training effectiveness. Emergency procedures were continually refined and enhanced based on operational experience, but these refinements could not address the fundamental, timing and decision-making challenges created by the aircraft's basic design characteristics. Documentation of emergency procedure effectiveness revealed systematic patterns of procedure failure that indicated fundamental incompatibility between procedural assumptions and aircraft emergency characteristics rather than inadequate procedure design or pilot training. Emergency situations consistently progressed too rapidly and created decision-making demands that exceeded the capabilities that emergency procedures assumed pilots would possess during crisis situations. The accumulation of operational experience and systematic analysis of incident patterns eventually provided institutional recognition of the fundamental design philosophy problems that had created the F-104's operational challenges. Rather than representing isolated technical problems or training deficiencies, the aircraft's safety record reflected systematic incompatibilities between design optimization principles and human operational requirements that could not be resolved through incremental improvements or enhanced training programs. Post-incident investigations revealed consistent patterns of pilot-aircraft interaction problems that occurred across different aircraft, pilots, operational environments, and time periods. These patterns indicated that the aircraft's operational challenges were not attributable to random mechanical failures, individual pilot errors, or specific operational circumstances, but rather reflected fundamental design characteristics that created predictable human factors problems regardless of pilot experience level or operational conditions. Investigation findings documented how the aircraft's design assumptions about pilot adaptability had systematically underestimated the cognitive and psychological challenges created by the aircraft's unique operational requirements. Pilots who had demonstrated exceptional competence on conventional aircraft consistently encountered difficulties with F-104 operations that were not attributable to inadequate training or personal limitations, but rather reflected the aircraft's fundamental incompatibility with human cognitive and physiological capabilities. The investigation process revealed institutional recognition that technological optimization could not be pursued without regard to human factors constraints, without creating systematic safety problems that exceeded the effectiveness of training or procedural solutions. The F-104's design represented an extreme example of engineering optimization that had pushed beyond the boundaries of human adaptability, while assuming that training and procedures could bridge any resulting gaps. Forensic analysis of accident sequences documented how the aircraft's design characteristics created decision-making scenarios, where pilot expertise became a liability rather than an asset. Experienced pilots who applied proven techniques often found these techniques creating additional hazards when applied to F-104 operations. This reversal of the normal relationship between pilot experience and operational safety indicated fundamental problems with the aircraft's human-machine interface design. The documentation of pilot reports and debriefing sessions revealed systematic communication problems between operational personnel and institutional leadership regarding the aircraft's operational challenges. Pilots consistently reported concerns about the aircraft's handling characteristics and operational limitations, but these reports were often interpreted as training deficiencies rather than fundamental design problems. This communication failure prevented institutional recognition of systematic safety problems until accident patterns provided undeniable evidence of fundamental design limitations. Investigation findings revealed how institutional assumptions about military pilot capabilities had created unrealistic expectations about human adaptability to extreme aircraft characteristics. The assumption that military pilots could adapt to any aircraft design provided adequate training and procedures failed to recognize that some aircraft designs created operational requirements that exceeded fundamental human capabilities regardless of training quality or pilot experience level. The analysis of training program effectiveness documented how conventional training methodologies were inadequate for preparing pilots to operate aircraft, whose characteristics violated fundamental assumptions embedded in pilot education and experience. Training programs that had proven effective for conventional aircraft created systematic preparation gaps when applied to aircraft whose operational requirements contradicted rather than enhanced conventional piloting principles. Long-term analysis revealed how the F-104's operational experience influenced subsequent aircraft design approaches and certification requirements. The recognition that design optimization could create systematic human factors problems led to increased emphasis on human factors integration during aircraft development, rather than assuming that human factors problems could be resolved through post-design training and procedural solutions. Regulatory response to the F-104's operational experience included enhanced requirements for human factors analysis during aircraft certification processes. These requirements reflected institutional recognition that aircraft design decisions created systematic effects on pilot workload, decision-making requirements, and emergency management capabilities that needed to be evaluated during design phases rather than addressed through operational solutions after aircraft deployment. The development of improved pilot training methodologies reflected lessons learned from the F-104's operational challenges regarding the limitations of conventional training approaches for aircraft with unusual characteristics. Training programs were enhanced to address psychological preparation for operating aircraft with unfamiliar handling characteristics, rather than assuming that technical training alone would provide adequate preparation for operational success. Simulator technology development was influenced by recognition that conventional simulation approaches had been inadequate for preparing pilots for the F-104's unique operational challenges. Enhanced simulation capabilities were developed to address not only technical aircraft characteristics, but also the psychological and decision-making challenges created by aircraft with unusual handling characteristics. Ejection seat technology development reflected lessons learned regarding the limitations of escape systems designed without adequate consideration of the aircraft operational scenarios where ejection would most likely be required. Subsequent ejection systems incorporated enhanced understanding of the relationship between aircraft emergency characteristics and ejection system operational requirements. Emergency procedure development methodologies were enhanced based on recognition that conventional procedure development approaches had been inadequate for aircraft whose emergency characteristics exceeded conventional assumptions about pilot capabilities and response timeframes. Enhanced procedures emphasized decision-making frameworks rather than mechanical procedure execution to address the cognitive challenges created by rapidly developing emergency situations. Maintenance training programs were modified based on recognition that aircraft with unusual operational characteristics created maintenance requirements and failure patterns that exceeded conventional maintenance training preparation. Enhanced maintenance training addressed not only technical procedures, but also the specialized knowledge required for maintaining aircraft, whose operational limitations created unique maintenance challenges. Ground crew training programs reflected similar enhancements based on recognition that aircraft with unusual characteristics created ground handling and operational support requirements that exceeded conventional training preparation. Enhanced ground crew training addressed the specialized knowledge and procedures required for supporting aircraft operations, with unique operational limitations and safety requirements. Medical emergency response training was enhanced based on analysis of F-104 ejection and accident outcomes that revealed injury patterns and survival scenarios that differed systematically from conventional aircraft emergency medical requirements. Enhanced medical training addressed the specialized treatment requirements created by advanced ejection systems and unique accident characteristics. Search and rescue coordination procedures were modified based on recognition that high-performance aircraft created emergency scenarios that exceeded conventional search and rescue assumptions about emergency location, timing, and survival requirements. Enhanced coordination procedures address the specialized challenges created by high-performance aircraft emergency characteristics. Institutional culture modifications reflected recognition that the traditional military aviation emphasis on pilot adaptation as the primary solution for aircraft operational challenges was inadequate for aircraft whose characteristics exceeded fundamental human capabilities. Cultural changes emphasized shared responsibility between aircraft designers and operational personnel for ensuring compatibility between aircraft characteristics and human operational requirements. Design philosophy evolution reflected fundamental recognition that technological optimization could not be pursued without systematic consideration of human factors constraints, without creating safety problems that exceeded the effectiveness of operational solutions. This recognition led to integrated design approaches that considered human factors requirements as fundamental design constraints rather than secondary considerations to be addressed through training and procedures. The broader aviation industry incorporated lessons from the F-104 experience into certification requirements and design standards that emphasized human factors integration throughout aircraft development processes rather than assuming that human factors problems could be resolved after design completion. These standards reflected recognition that some design decisions created irreversible human factors problems that could not be addressed through operational solutions. Pilot selection and career development programs incorporated enhanced understanding of the relationship between pilot psychological characteristics and adaptability to aircraft with unusual operational requirements. Selection criteria were modified to address not only technical competence, but also psychological flexibility and adaptability to unconventional operational scenarios. International cooperation in aircraft development reflected lessons learned regarding the importance of sharing operational experience and human factors knowledge across national boundaries, rather than assuming that technical specifications alone provided adequate information for successful aircraft operation. Enhanced cooperation addressed the specialized knowledge transfer required for aircraft with unique operational characteristics. The F-104's legacy in military aviation included recognition that the pursuit of maximum technical performance could create aircraft that were fundamentally incompatible with human operational requirements regardless of training quality or operational procedure effectiveness. This recognition influenced subsequent military aircraft development to emphasize operational effectiveness rather than pure technical optimization as the primary design criterion. Civilian aviation applications of lessons learned from F-104 operations included enhanced emphasis on human factors considerations in high-performance civilian aircraft design and certification. The recognition that design optimization could create systematic human factors problems influenced civilian aviation standards to prevent similar problems in civilian aircraft development. Educational program development in aeronautical engineering incorporated F-104 experience as an example of the systematic problems that could result when human factors considerations were subordinated to technical optimization during aircraft design processes. Educational programs emphasized integrated design approaches that considered human factors as fundamental design constraints from initial design phases. research program development in human factors and aviation psychology was influenced by recognition of the limitations in understanding human adaptability to extreme aircraft characteristics that had contributed to F-104 operational problems. Enhanced research programs addressed fundamental questions about human capabilities and limitations in high-performance aircraft operations. The systematic analysis of F-104 operations provided institutional recognition that the aircraft's operational challenges were not attributable to inadequate human performance, but rather reflected fundamental design decisions that had created operational requirements exceeding human capabilities. This recognition represented a fundamental shift from blaming operational problems on human limitations to recognizing design responsibility for ensuring compatibility between aircraft characteristics and human operational capabilities. The F-104 experience demonstrated that engineering excellence in achieving design optimization goals was insufficient for operational success if the optimization process failed to account for human factors constraints that could not be overcome through training or procedural solutions. This demonstration influenced subsequent aircraft development to emphasize integrated design approaches that considered human factors requirements as fundamental design specifications rather than secondary considerations. The ultimate lesson from F-104 operations was that aircraft design optimization must remain within the boundaries of human adaptability to create operationally successful systems. When design optimization exceeded these boundaries, the resulting aircraft created systematic operational challenges that could not be resolved through improvements in training, procedures, or operational techniques, regardless of the resources applied to such solutions. This lesson fundamentally influenced military and civilian aviation approaches to aircraft design and certification, establishing human factors compatibility as a fundamental requirement for operational aircraft rather than an optional consideration that could be addressed through post-design solutions.